So recording started now. So now a little bit review about the previous lecture about filtering enhancement, that you have noise and artifacts in the image, and we want to get rid of it. And when we apply the filters, what we get, ideally what we want is a noise-free, perfect image. But the reality is mostly something else, and that is we have an image which is a little bit less noisy. And if you have a bad filter, you actually enhance the noise, and that doesn't make sense. So please don't do something like that. And let's see. So what we get, if we have an image modality, we get some kind of image. This is just an illustration, so it's a cartoon. But anyway, so let's say we get this cell image from our modality, and it gives us a bunch of gray levels that represent the response of the object with the incoming radiation, illumination, whatever. And here we can see that levels in this image are distributed over the intensity range available. So in this case, we are talking about absorption coefficients, and apparently here they range from 0 to 1. In most images, they don't range from 0 to 4. Usually it ranges from something else that's determined by the interactions. So what we can do, we can count stuff by the human eye, also just seeing, okay, there is one, there is one, there is one. Then we come to the uncertain cases, there is maybe one. And we can also qualitatively describe, there are a little bit more of this feature in the image or a little bit more of that, and the structures have some kind of shape or whatever. And let's see if I can move this one up. And what we want to do is more like getting some real metrics out of it. And on the way to getting these metrics, we have to apply a set of different methods. And depending on your background, you may choose a different set of methods. So there can be the experimentalist approach, which actually goes directly to connect it to what you expect in your field of research. Can be the computer vision approach, which looks for so abstract structures like lines, shapes, etc. And deep learning approach, then you let the data teach you what you want to see. So these are the different approaches that you can choose among. Often it's actually a mix of it. And because you want to have a result that actually in the end applies to what you want. And on the other side, you need to apply some kind of algorithmic approach also to learn what's going on, or to extract the information that you can use. The model-based approach is you have some kind of excitation, which goes through the sample, which gives you some kind of response. And this is captured by the detector. And this can be more or less similar, summarized with this equation, that you have some system, you have a stimulus and a sample, and then you get the measured information. Oh, here wasn't so much space. Okay, so here is a little example. You have a beam profile, and you have the true sample profile, so that is the real world thing. And when you investigate this sample with that beam profile, you get an image looking like this on the detector. And that sometimes can make sense, sometimes it doesn't directly make sense, because you have to do some reconstruction approach or normalizations in order to get the information you want. And then in absorption imaging, which is done quite a lot, X-rays, neutrons, ultrasound, and so on, then you usually have the Beer-Lambert's law that describes how the detector reacts. So you have the source intensity, and you have some sample response. This is mostly actually a line integral through the sample. Here it's very simplified, so it just have an attenuation coefficient and the thickness. And from this, we want to identify two distinct components, or maybe even more distinct components, and they should be somehow related to what the method sees. Oops. So, and yeah, here is the example. Now I'm building up an example with mammography. So we have, again, the equation of the detector signal, which is actually an image. So it's the attenuation coefficients at different positions and the thicknesses at different positions too. And together, then we get the line integral that I was talking about just before. And what does this segmentation give us now? If you have a color image, you have usually three color channels, RGB, red, green, and blue. You can have a spectrum for hyperspectral imaging. So, and there are different methods for doing that. Most close to me is actually spectral neutron imaging, where you can look at material properties. You can look at stress and strain within the sample by observing the shape of the spectrum. And you can also have some vector tensor field that you want to look at. And from this information, you want to extract just a few discrete values. Is it background? Is it sample? Is it a flaw? Is it some other anomaly? And when you do this, you reduce the 32 bit you had before per pixel, reduce it down to 1 bit or maybe 2 bits. And all of a sudden, you have reduced also your data size from the 56 gigabytes per sample down to 1.75 gigabytes. And then it's getting more handleable in any computer. Gigabytes is usually quite hard for many computers to work with. And that one you can, the later one you can probably work with in most laptops today. When we are segmenting cells, we look at, again, the illumination. We can see that some the cells absorb light and resolve regions in the image, and lighter regions doesn't have any cells at all. So that is what we would look at in such images. Oops, and there I was supposed to show you this. And here you can see an image of a cell colony, and all the black ones are the cells. And if you look at the histogram of this, you can see there is a lot of background. So all these pixels here correspond to all the bright. And down in this tail is where you would expect where the cells are. And how would you now select the pixels that are cells? So can anyone maybe give a suggestion? So, yes? Yes. So, for example, setting a threshold somewhere around here, I would think is reasonable, and that would separate it into pixels that are cells and that are background. We will look at methods doing this a little bit later and also next week. And we will see how the performance can be affected by that. And here we have this mapping where we have some, let's see here now. Yeah, this is a vector format, okay. In this case, we have 2 values for each pixel. So we have some detector value and we have X and Y vector and of course the position. What you see here in this table is just a selection out of many, many pixels in the image. And hey, doesn't move on. Why not? Okay. And looking at these data in something called a co-location histogram, then we can compare all the information we have in these images against each other. And in the diagonal, we have just the, the information itself. So each column in this table. And then we can look at X versus Y, and then you see that we fill up the whole field. We can look at the detector value versus X. We have an X vector, we have a Y vector, and we can compare all those against each other. And that gives you an idea. If you have many values in a table, then that gives you already visually an idea which combinations actually give you information that is relevant. Sometimes it just looks like gibberish. And sometimes you can see here, for example, if you connect the Y vector with the X vector, you get a circle. So that is actually a structured information you can get out from this table. And sometimes it's actually relevant to use it. Other cases you can see here that if you compare, let's see what this is, that's the detector value versus the itself. What? No, Y, yes. And here you have it versus X, and you can see that everything is kind of compacted towards the left side of the histogram. So this is a way to look at many data columns, and it can actually help you to find the right information. Yeah. My forwarder doesn't want to. And looking at the vector field, it as vector field, now I'm just looking at the X and Y vectors. You can see that is some kind of field that is beaming out from the center. And then we can apply thresholds to this. For example, orientation-wise, that if X component is greater than 25 and the Y component is greater than 25, then we set it as 1, or otherwise we set a 0. And that would segment us something like this, where we have this part of the region. We can focus on some spatial information in this data. And another way to look at it, let's see, is to look at the joint probability. We can see here, if we threshold the circle, then we can also get this information out from the plot. Now we can also look at the information value. If fx and y times the intensity is greater than 1, then we set is equal to 1. Then we set it as 1. Otherwise, we don't set. We set a 0. And here is another one, also direction or orientation. The way we look at the orientation vector, looking at angles, so we can select an angular range if we like. So if you have vector fields, you can do a lot of these manipulations in your segmentation. And that gives you segmentation possibilities based on orientations. And I think that was the last slide of this part. It is, yes. Okay. Let's move on to the second part. And now we look into how we can quantify and evaluate, and that is the machine learning approach, how to evaluate what we are doing actually. And first, we have something that learns and look and identifies these segmented regions. And one example would be here in electron microscopy, where you have an image of cells of a cell, and you want to identify where you have the mitochondria in it. And what we want to see, what we want to do is to identify where are the mitochondria and classify them as background and everything else in this jitter of information. Yeah, there it is. In this jitter of information, we want to set all that to 0 and only get these white blobs here as relevant information. And how we want to quantify this and how good we are, we can divide it into 4 different classes. We have true positive, which are the ones that are labeled as mitochondria and actually are mitochondria. Then we have true negative, the ones that are labeled as background and actually also are background. Then we have 2, call it bad cases. That's a false positive. That is classified as it would be positive, so as it would be a mitochondria, but it is not. And the other one is the false negative. That is where we miss to say that it is a mitochondria. And looking at applying a threshold on the image, we can say, look at this histogram here, and we see, okay, this can be a good threshold. I think I just set it by random. More usually, what you would do if you have a histogram like this is to put it precisely in the valley between. But in this case, it may be that the mitochondria have a little bit higher intensities than the rest. So that's why we set a little bit higher. And what we get is an image like this. And this is what we expected. So this is not really a good segmentation. And now let's look at what, oops, no, sorry. So now let's look at the performance of the segmentation. We have the true negative. So this is the confusion matrix that we already looked at. And here we have the true negative image. And you can see that there is a lot of the white. We have the false positive here. So there is a lot of walls. They were actually marked up as being a mitochondria, but have more or less the same gray level. False negative is not that much because we set the threshold relatively high. And that's why we also got not so many of that. And then we have the true positive. And we see that with this threshold, we actually get pretty good true positive. But these parts here, they are not so convincing. And we can also look at this in more, put it a bit of numbers on it. And then we can see that we have about 60% is true negative. We have 32% false positive, which is a lot. In particular, compared to the class itself, where you have 7% true positive. And from that, we also can draw a heat map where you can see where it happens that you do the wrong classifications. And I have here the 4 colors. White is true positive, red false positive, blue false negative, and black true negative. And you can see that, well, a lot of the red on the walls, which we can expect, are actually bad. But also from the gray level, it's very hard to distinguish between them. And then within the mitochondria, you can see that there are the fluctuations in the mitochondria. They appear as sometimes as false negative. What we also look at are some metrics based on true positives and false. And one is called recall or sensitivity. So that's the true positives over all that should belong to the class. And then we have the precision, which is true positive over all the pixels that were labeled as positive. And these two together are very often used in machine learning to tell about the performance of the segmentation. And at the example we had with this mitochondria, I calculated the recall and precision, and we see that the recall, it's actually pretty good, hits the mitochondria, but the precision is pretty bad. And that actually also reflects what we saw here in the previous image, that, well, we are actually pretty good with all the white spots for the mitochondria. So the recall is good in that sense, but as we have so much red in this image, the precision is bad. Another way to illustrate this is to use the receiver operating characteristic called ROC. And that is originally something that was developed in World War II in the detection theory used for radar detection of aircraft. And it shows the performance of your detection system. And if we just would put a single threshold at 50%, so it's more or less, that's the same as flipping a coin, uniform distribution, random guessing more or less. And this can be drawn in this curve, and the ROC curve shows the relation between precision and recall in the segmentation. So let's look at the hit and miss statistics of our data. This is a long table. We can see small details, but the interesting thing is if we plot this, we can see different performances, and in the ROC curve, you have on one side here, you have the positive rate, so the recall, and on this side, you have the negative false positive rate, and that's the precision. And ideally, you should have 100% true positive, and you shouldn't have any false positive at all. In our specific case, we had a dot on this spot, but that's only one point, and that's no curve. So what you do when you compute the ROC curve is you test all thresholds and see what that gives you in terms of precision and recall. And doing that, we could get, for example, a curve like this, where you can see that, okay, for low thresholds, we have underestimated the true positives, but the false positive rate is also pretty low. And if you go up here, you have detected everything, but the false positive rate is pretty high too. So that's also not so good. If you're setting up a system, you have to decide what is more dangerous, damaging, having too few false positives, too few true positives, or too many false classifications. And here you can also see are clearly better in this segmentation than just random guessing. And that's good. If you would get an ROC curve that is below random guessing, it's time to reconsider and redesign your segmentation method. And here we can look at what effect do we have of using different filters on our image. And again, we have the ground truth map. This is what we expect. If we have no filter, then we should be something that looks like this. If we applying some blurring and reducing some noise, then for the playing, we also do difference of Gaussian filter. So that's an edge detection filter. And then finally, we also have a median filter. And now we want to look at the segmentation performance if we apply our segmentation on these images. And what we see is that, let's see, we have the blue one is no filter at all. And it's what we saw before. If you apply a Gaussian filter, you are in the yellow curve, and that looks pretty good because now you have a very rapid increase here in the true positives without having too many false positives. With median, you're a little bit improved, but not as much as with the Gaussian. And in the case of using the difference of Gaussian, then it didn't work very well. It's actually oscillates around really what we want to see. A perfect ROC curve would actually be that you go straight from 0 to 1 with almost no change in the false positive rate. So ideally, you want to bring your ROC curve as close to this plus up here. Then you have a really good system. But these are curves, and it's maybe not so easy to work with curves because you want to put numbers on the performance in some sense. And what we use then is area under curve and using that as our metric to tell if our segmentation is doing what we expect it to. And here you can see the areas under different curves. And if we measure it, you can see that no filter and Gaussian and median, almost the same. You can also see what we visually could also tell that the Gaussian is a bit better. And you can see that the difference of Gaussians is definitely performing the work. So this is a metric that is used in machine learning algorithms during training, actually, as one of the metrics that they control the training progress with. Another thing that very often occurs is that you want to segment multiple phases. So you have not only mitochondria background, but you may want to have something else too. And that is when we come into segmenting multiple phases. And here is a piece of shale, was measured in a synchrotron X-ray tomography experiment. And in this image, we have 3 different components. We have clay, we have rock, and we have air. And now is the question how we can separate these. And on your own screen, you can see it much better than here now. But there are bright regions, there are background, which is the clay. So the bright regions are bones, the rocks. And then we have the clay. And in here, there are also some voids, but under these light conditions, it's hard to see on the beamer. And looking at the histogram, we want to find 3 different classes. And again, maybe I can get some suggestions where these different categories should be placed as thresholds in the histogram. This is, by the way, not an easy histogram to work with, but maybe you can have an idea anyway where you would like to put these thresholds. Yeah, there it is. So one would be around here and one here. Makes sense, yes, because both the voids and the rock pieces are very underrepresented compared to the background clay. So that is makes sense to do a thresholding like that. So let's put the thresholds in like this. I had one at 0.3 and one at 0.5. And then we have this our categories. And if we do this, we get segmented images. And it looks like it makes sense in this case. One thing is when you have images like this, where you have very small dots, it's very hard to fill images if they are noisy. So there you have to be very careful. I mean, if you want to, this actually looks very much like some kind of rock here. No, no, wait, I must have put the labels wrong. Oh, it's confusingly close. Okay. Anyway, so here you have a rock piece, and it actually makes sense that you have it. But if you apply a filter that smooths everything, then it's very soon that you would actually smooth so much that you would kill information that you want to see. And if you want to now implement a thresholding with your own code, there are different ways of doing it in different programming languages. And in Python, in particular when you're using NumPy, and in MATLAB, it's very easy. You just say that you have the gray level image greater than the threshold, and then you get your thresholded image. That's one line. If you want to do a more complicated threshold, then you can maybe do something that you have threshold 1 and threshold 2, and then you combine the two. So that is logical, no, a Boolean AND that you have here. If you don't have NumPy, it's a bit more complicated, and you can use some kind of mapping and lambda function combination that does this work for you. But mostly today, we are actually using NumPy. So this is more an outdated curiosity that you can do it like this. If you want to do it in, say, traditional programming languages like Java and C, then you have to write a lot of loops for doing this. In particular, if you just want to segment a certain region of your image, if you want to segment all pixels, it's a very simple one, then it's a single loop. But in this case, if you have marked up a region from min-max in X and Y set, then you have to compute some offset, and the offset says the position, and then you have to compare the position with the threshold. And same goes also for C. And here in C, you also, now in both cases, you also have to allocate the destination volume that you are working with. Next, it's actually a good time to take a break. So let's take a break, and Afterwards, we are going to talk about morphological image processing.